Okay, good afternoon. It's good to see people here. Hopefully, a few others will be joining in the coming minutes. Today, I'd like to continue on uh, a thread that we alluded to within the last lecture. The last lecture on Friday, I had spoken about hybrid modeling, and I covered uh, several compelling strategies for mixing together just different system science approaches. Uh, what it did not do, however, was to have a chance to cover uh, those other approaches in any sort of detail. And considering the options for today, I elected to secure that thread of continuity by using today to expand on understanding of one of the prominent two types of modeling combined with agent-based modeling, namely discrete event simulation. This discussion will build on some remarks I've made through the semester, and especially at the beginning of the semester, on trade-offs between multiple methodologies. But we'll go into more fine-grained detail. And it also sets the stage for this week's lab, which will involve elements of discrete event simulation. Now, to that end, I'm going to be showing some slides, but also working through an example as part of this lecture to illustrate some of the concepts and to make them more concrete. Now, discrete event simulation is a close cousin of agent-based modeling in some ways, and very distinct with big contrasts in other ways. In a certain sense, agent-based modeling is more, I should clarify, all system science dynamic modeling traditions share essential features. They all share a way of characterizing the current state, characterizing how, given the current state, the state evolves. But they do so with very different languages and motivated by quite different questions, more distinctly. The types of questions they seek to answer are actually rather different. From a certain perspective, if we're to distinguish among system science dynamic modeling approaches, agent-based modeling, system dynamics, stock and flow modeling, and discrete event simulation, you can make a case that by certain standard, agent-based modeling and discrete event simulation are discrete event simulation is the closest other tradition to ABM. You can make a different case that no, in fact, the closest one is stock and flow model at a certain level. But there are certainly many threads of similarity between discrete event simulation and ABM. Both are individual-based traditions. Both are capable as such as characterizing aspects of heterogeneity, history dependence, and can depict spatial context. They can capture spatial mobility in really rich ways. And they can look at they can answer fine-grained questions about the impact of resources or types of actors within a system and help in prioritizing those. In some ways, they're quite different, and I'll emphasize some of that, but the sort of gist of it, the most critical difference, I think, is the scope of what they include, what they seek to include. With discrete event simulation, it's much more contained. It's much more more tightly scoped the sort of questions that it seeks to answer. So discrete event simulation really is a workflow, and this title says it all. It concerns resource-constrained progression of, you could call them agents. Any logic actually will use that term sometimes, but progression of entities, or you could be forgiven for calling them actors, but they're awfully passive actors along structured workflows. So let me say that again. It involves workflows like this, and entities progress along those workflows in ways that are constrained by availability of resources. If resources are unavailable, they will queue up within the system and await availability of resources to a point, at which point they might leave the system through leaving without being seen or what have you. Now, these workflows need not be linear. They can contain branches, they can contain merges, they can contain loops, and the routing can depend on aspects of an agent's characteristics or history in ways that is quite fine-grained. But there's a fundamental asymmetry here between the entities who progress along here. Think patients, think cars and assembly line, think individuals applying for social assistance, think individuals going through a set of processes involving application to some program. So contrast between those individuals on the one hand and the resources that are needed to allow them to progress. Mehdi, maybe you could. So what does this give us? This gives us this system, in contrast to agent-based modeling, which is a very wide potential scope, a very broad series of possible applications. By configuring an agent-based model with its quite broad vocabulary, we can build up, in sort of the grammar of agent-based modeling, we can build up very articulated, textured, rich depictions of a vast array of types of scenarios. By contrast, discrete event simulation is really quite focused on this issue of entity progression along resource-constrained pathways. And that focus is not so much a limitation. You could think of it as, you could be forgiven for thinking of it as a limitation. On the other hand, it's an asset from a certain liability. A liability from some perspectives is an asset from another. It's an asset in that it gives us enormous capability to crisply, expressively characterize with a very concise means the problems of this sort. Resource-constrained progression of entities along these workflows. We could specify them with great specificity, transparency, conciseness, expressiveness. And so doing, we can identify the impacts of resource availability, resource placement, resource coordination, joint resource availability, resource prioritization on that workflow. And even things like facility layout. The layout of a facility spatially can be readily factored in ways that help us understand how does that layout impact the progression of agents along said workflows. Okay. I will also say, compared to agent-based modeling, and more akin to stock and flow modeling, discrete event simulation, the amount of programming required, about software engineering required, is much less than for agent-based modeling. Agent-based modeling in its current predicament, its current incarnation, requires a great deal of software engineering to build large models. And to build smaller models, it still requires some elements of it. You could be forgiven for think of it as similar to, creating things in R. You require some coding to manipulate those data frames and analyze them commonly. And an age-based model is a bit like that. Now, I'm working in our work to move beyond that and making it much more declarative and to really minimize the traditional programming required, focus on the specification of what you wish to characterize. But the current state of things, unfortunately, involves software engineering for medium and large scale projects in ways that are central to delivery. It involves some degree of managing the programming in a structured way so that it doesn't overwhelm the focus on the model. For medium and large scale models, it's a sizable issue, and for models that evolve for a long time. Okay, so I've talked a bunch here. Let's go open a model. I've sort of gestured at some things. I'd like you to go help example models, and I'd like you to scroll down to Trauma Center. Should be down here. So again, I'm looking these examples over to the right here. And if you open Trauma Center, you should get something such as this opened. This model is going to characterize a facility, and we'll see that facility, not surprisingly, perhaps, lives in Maine in this overall environment. That much it has in common with agent-based models. And if you go and zoom in on it, and I will seek to do so here, if I can avoid pressing the wrong widgets. Okay, somehow my widget pressing is impaired by Zoom. Here we go. What you can see is a facility. We're laid out. We'll find out that these sort of tracks route people around. It has many different types of areas in it, which it turns out are colored in a way that distinguishes types of fixed resources, things like rooms or fixed equipment, such as X-ray machines. There's an express care area, an emergency department, X-ray, some areas for certain more specialized care, such as types of scanners, such as VQ scanners, ultrasound scanners, etc. And there's types of entryways for things such as ambulances or walk-ins. There's waiting rooms and triage nurses and receptionists, and people admitted from the trauma center over here to a hospital, whose depiction is not here. We're going to go through some elements of it. I will note that behind this is a set of logic. So this is a visual presentation. This characterizes the visual environment. By contrast, the underlying logic of this is shown here. So here we have logic involving, so where did I go? I scrolled down here. Patient arrival. People arrive either via walk-in or via ambulance, and there's a different triage process for ambulance associated with the emergency department versus for walk-in individuals who go through registration and go to a waiting room. They interact with the registrar, and before that, they're triaged as to level of urgency, such as the CTAS scale here in Canada, the Canadian Triage Acuity Scale. Now, if they're using the express care, they They undergo a specific workflow for that. As it turns out, that will be time limited. And otherwise, they come down and are routed to the emergency department in a way that awaits emergency department room. They go to the room and they go through a workup, and potentially a specialist is required. It may be that certain orders are required. It may also be some imaging is required. And under certain circumstances, more specialized imaging, such as with CAT scans, VQ scans, which I believe are used to capture elements of perhaps pulmonary embolism or heart issues. I can't recall. And ultrasound scanning is conducted. And then there's kind of a review by a physician and either admission to the hospital or discharge. So as you could see, there's a rather articulated workflow here. But what's to be emphasized is, per my original comments, the flow through that workflow is resource constrained. So in those blocks are various requirements for having access to or seizing resources, seizing triage rooms, for example, seizing, being allocated a nurse, awaiting availability of an ultrasound machine or an X-ray process. And these are characterized hierarchically in ways that abstract away from the details for this, but in a way that can be plugged in there. They're also requiring a physician assistant, etc. Okay, so let's. I'm going to zoom out here, and I think we'll do well to run this. So I'm going to right-click on simulation here, and I'm going to say run. And this will give us a sense of some of the implied dynamics, and I'll use it to depict some sort of affordances and some of the drivers for those dynamics behind the scene. Okay, so here we have a 3D depiction of our trauma center, which is a depiction utilizing 3D rendering. What we see here is some movements of individuals within the facility. Ambulances come in, drop off patients. Other patients come to this waiting area, await interaction with the registrar. And those patients are then routed by various care personnel according to their condition to various procedure rooms or workup rooms within the facility. It may be easier to see here in terms of division of kind of responsibilities for those areas to see it here. Do remember that these rooms play a role of resources. They are fixed, that is stationary resources. And individuals need to await the availability of resource if they're already full. So individuals may await up in this waiting room before they can be processed by the registrar or before a room is availability, etc. So the coordination here is dependent on a wide set of resources. I will note that said resources are of many different sorts. So we have specialist individuals, doctors, physicians, assistants, nurses, registrars, technicians, CAT, particular types of technicians for the different types of machines. And in fact, you could see resource pools here, which delineate different commoditized sets of resources of different sorts. So those are all in the background. Behind the scenes here, individuals are progressing along these workflows that we saw earlier, progressing along them in ways that are awaiting availability of resources. Here, we could see something about the resources, their level of availability, their level, I should say, of utilization, the degree to which resources are in fact being used over some time averaged way. So, for example, nurses here, You could see at any one time how many nurses are engaged in actual delivery of care at that time. This has utilization of somewhere above 60%, and hence the color here. Some of these resources are more heavily engaged. Perhaps surprisingly, triage nurses are less so. And some, such as the bed in the block care unit, or bed for ultrasound technicians, are actually quite minimally utilized as it stands right now. There are statistics which express this. So here, in terms of the arrival rate, which is driving this, we can characterize the utilization of these resources graphically. This is providing an assumption like the arrival rate, an exogenous assumption about the distribution of people who are seen and their level of acuity, their level of severity. This is also an assumption in terms of opening hours. We can change that assumption and see how it affects the utilization, for example. Others of these things are emergent. The utilization is emergent. That comes from, the competing availability of different resources for serving patients, the fact that certain resources may be more bottlenecks than others, that patients may be awaiting a bed much more so than they're waiting a specialist physician, et cetera. The fact that they need one resource before the other may mean the first is more of a bottleneck than the second. But also what emerges is length of stay, for example, for types of individuals here in the express care and the emergency department. And this can give us a sense of, how certain resources may be serving as in a constricting way in terms of availability. Okay, so we have these workflows, these processes by which entities, so I'm going to drill down now a little bit more, having circled on a higher level. Now let's talk about these workflows. Okay, these workflows, sometime I'll fall into calling them flow charts. Workflow is the better name. There's processes scattered throughout these blocks or operators indicate processes of sorts. Sometimes they're hierarchically described. There's maybe a sub-workflow in there. There are queues associated with awaiting certain processes, awaiting availability of the registrar, for example, awaiting ability of triage room. There are limited resources. We saw that here. We have a certain number of nurses, a certain number of physicians assistants, certain number of specialists. And if we were to increase the number of resources of nurses, for example, we would expect to see a lowering of their utilization, the fraction of their time that they are utilized, because there's more to go around to handle the work. There's spatial mobility of entities. We saw that earlier, right? These entities are coming in and moving around. Many of the individuals moving here, if I could slow this down, are actually resources. They're mobile resources. They are resources with agency, physicians, nurses, physicians' assistants, potentially technicians, etc. By contrast, some of the individuals here may be at any one time patients. So there's a patient waiting or a would-be patient. So that is in fact an entity. Here we see a resource accompanying an entity. That resource is needed to escort the entity. They attach, as we say, to the entity move them to a certain location. But you have to recognize that even though they move together, they are two ontologically different types of things. One is a patient, one that is an entity flowing through these workflows, and another is a resource that is needed to allow some of these blocks to be reached in order to allow, for example, this triage process to take place. They have to seize a triage room, and they have to go to the triage room. They may, in some cases, seize an express care room, and they are accompanied in such process by a nurse that is later released. So, in short, although you may see different icons moving around, just be aware they're two very different sets ontologically. There's the entities flowing through this, and then there's the resources that allow them to flow through this and allow them to undergo the movements which are needed to route them through this, to go, in fact, to the waiting room, to go, in fact, to the triage area, to go, in fact, to the emergency or the express care room. They may need resources to accompany them. So, one thing you're seeing very different from agent-based modeling is this kind of dichotomization between, on the one hand, entities moving around, getting operated upon in these workflow processes, being routed through here, resources which are serving the needs for those entities, which may have some workup processes themselves, but their fundamental job is to allow the entities to progress along this structured workflow. Those exist in they're very different levels of or roles that they play in the system. And much of our interest lies in understanding how long it takes an entity to go from start to finish, their average amount of time, or how many entities we can treat per day, or how availability of different resources shapes how those things, how quickly they can go, how many we can go per day, or how placement of the resources or placement of mobile resources or placement of portable resources like ultrasound machines can facilitate this process. If we were to schedule, to place the X-ray machine more centrally versus peripherally, how much of a time difference would that make in entity movement? Entity movement here is endogenous. It's not something that's pre-programmed. Their speed of routing is pre-programmed, but moving at any one time when they are moving. But because they are being blocked at various points in said process, because they are awaiting resources, because they have to move in the facility in a wheelchair or gurney or by walking or what have you, they will take a certain amount of time to even move around. And all of that leads to the time that an entity spends within this workflow or within this structured workflow to be different depending on availability of resources, placement of resources, et cetera. And we can examine that. Okay, we've had a bit of a glimpse at this running model. We can stop there. We've seen how it can be used to add what-if questions, and I want to talk a little bit more. So during these workflows, entities are allocated to, resources are allocated to fixed resources like triage rooms, mobile resources like nurses, or a registrar. Here, the registrar's time, or portable resources like ultrasound machines that could be brought to the entity. We can capture those allocations of resources. Those often use the term seize. They're seized, and it's not meant to imply a transgressive process, but one where there's an allocation going on. Entities commonly move around spatially, but they are often attached to resources. For example, attached to a gurney, attached to a wheelchair, attached to a nurse, attached to a physician who accompanies them. And therefore, whither the entity goes, there goes the resource with it, because they are allocated to the resource and they are attached to the resource. In other cases, the resource may be mobile, may not be attached to the entity, but may instead go be fetching things for that entity, fetching a ultrasound machine or an ECG to be able to test the agent's heart. So we've seen flowcharts specify workflows, a process through a process. These are structured workflows, much more so than we have in agent-based modeling, right? In agent-based modeling, we have different types of resources, but there's not as much kind of a defined workflow of many, many, many steps that they go through waiting at each stage. Resources are required for proceeding at workflows. We could, in principle, have those resources in an agent-based model. In principle, it certainly has the capacity to represent that. But that workflow processing would require quite a bit of code to capture availability of a resource. Entities interact here with resources, seizing them for allocation of those resources, or attaching, detaching for moving physically together. There's physical homes for resources. So, for example, here within that model that we saw, if we scroll up here within this depiction, we may have, for example, a nurse's lounge in some areas of the facility. For example, a doctor's room or a nurse's room, where doctors and nurses can go put their personal effects, rest between shifts, take a nap if necessary, etc. And similarly, certain resources live at defined places, right? Like X-ray machines, which are immobile, or CAT scanners, which are immobile. Okay, continuing on, I will note that commonly in these environments, we have these sort of lines, which are, in fact, they may look decorative, but they're, in fact, based on markup of the space to delineate paths through the space. They're a graph connecting, they're an undirected graph connecting one area to another. And the existence of this sort of line, this sort of segment between different areas indicates the possibility of walking or traveling along it. So the fact that we saw, not 5 minutes thence, individuals traveling along this thoroughfare, or traveling along here, or traveling over to here to this waiting room. The fact that they traversed exactly these paths was not an accident. It was a reflection of these delineated segments by which we can route individuals. And those segments allow, in the language of of discrete event simulation, to say, bring this person to a certain destination, and it will figure out a route, typically the shortest route, that will get them from A to B. So maybe they have to go to this procedure room, and it knows, well, I could go this way more quickly than I could go this way down to the procedure room. So again, emphasizing this here, we could go look, and again, you will see people moving along exactly these paths into certain areas. That is the hidden logic by which they move, and they are routed from A to B because it knows where they are now and where they want to go, and it will take care of routing them at a speed dictated by the agent. So if you look at simulation, you look at speed, there's parameterization of the speed of staff and how fast they walk with the patient, and the speed of patients independently. You can imagine further characterizing the speed of a resource such as a gurney, a type of bed, or the speed of a wheelchair, for example. You could further characterize. Okay, I'll pause this here, and we will go back to characterizing this. Okay, so again, terminology. Entities are the parties in which the processes operate. By processes, I'm talking about these operators, these blocks. They operate upon entities. The entities flow in and are operated upon here and in queue when they're waiting availability of a resource. They proceed along in a way that's resource mediated. The entities are predominantly passive here. They are indeed operated upon. Contrast that with ABM. In ABM, there's a sense of, among agents, of agency. Agents interact with each other. They progress in ways that are shaped by perception or decision-making. They interact with each other and with the environment with a sense of agency. They are active entities in the system, active actors. By contrast here, these entities flow through and are routed by the flowcharts. Do people interact here? They do, but they interact in one defining way. These different patients arriving through ambulance and through walk-in, do they interact? Absolutely. And through one mechanism, applied again and again and again. They keep each other waiting. They are typically not interacting by word of mouth. They're not interacting by spreading pathogen. They're not interacting by one individual, affecting the judgment of another or encouraging them to leave from an overcrowded emergency department saying, I'm out of here. Generally, those types of considerations are outside the scope of this model. Those start to get into the territory of agent-based modeling or, appropriately enough, hybrid modeling. By contrast, here, entities interact in one very big way. They compete for resources. They keep each other waiting. Okay. So here, there's typically multiple entities flowing through, right? They're queuing up and awaiting resources. The fact that you're in the X-ray machine now means that I have to wait, or in the CAT scan now means I have to wait. The fact that I may have a nurse now assigned to me means that you may not yet have one assigned to you. The fact that I have a bed assigned to me in the ER means maybe you're still waiting in the seats. Entities are often associated with the location and physical representation, which travels around. We've seen that. If you wish to characterize additional attributes of an entity, you can do so by what's called subclassing. So you can, instead of saying this is a generic entity, we can say this is a patient entity which additionally has these characteristics. And that could allow us to keep track of everything from fixed characteristics, perhaps age or underlying conditions or an individual's presentation, how they present in terms of gender. It could provide indications of their attitude towards retaining, staying there for long periods despite long waits. Their attitudes towards care and continuity in terms of remaining despite long waiting times. Okay, let's talk about these workflows. Workflows commonly enter via some sort of mechanism. This could be a more anonymous sort of source. It can also be a type of entry point which is more suitable for hybrid modeling, where agents could enroll themselves in it. Some of these are more, and I believe it's the source, is more, you could specify distribution or a certain rate at which entities come in, an inter-arrival time. By contrast, others, for example, agents in an agent-based model can enroll themselves. And indeed, that's a key nexus within hybrid of DES and agent-based modeling. So they can come in, and normally they flow in a single direction. That's not uniformly true. You can have loops. You can have looping back to an earlier location, but generally you're not going to have them flowing in the opposite direction. You can just have loop back to a certain point and sort of loop around under certain conditions, so waiting for, successive tests to be run or imaging types of imaging to be conducted. The type of operator or block is shown graphically. This is actually a somewhat older depiction. And then they'll often leave by one or more sinks or places that they leave this network. And again, that can be different in hybrid modeling, where they will leave without entirely disappearing from the model, or in more classic DES, they will disappear from the model's concern outside the scope of the model when they reach the sink. These flowcharts, as I mentioned, can be hierarchical. They can have branches. They can have joins. And in our process modeling context, we will often turn to the palette that will allow us to characterize this. And here it will be the process modeling library. Here in mine, it's up at the top. It's possible you will need to press this little button down here, a little plus on yours to add it if it's not there. The process modeling library will give us these sources, these sinks, these delays, these queues, these sort of branching points, and these various types of operators. And you can hold your mouse over them to find descriptions. Some of these are more specialized, and I won't get into them. For example, batching and unbatching can be quite useful when you have more flows of materials, and you might have a palette of things that are batched together, and then they're unbatched. But there's a set of sort of these top ones that are often, quite a few of these are more critical. Not all, I'd say split and combine, assembler are a little bit less commonly used in sort of basic service workflows. Okay, let's talk about resources. I noted some distinctions among resources. I've sort of said enough about resources, I think, to give you an idea of what they represent. But there's distinctions among these resources. So again, we have entities which flow through. Resources are needed for those entities to make progress. But among resources, there are distinctions. There are mobile resources, those with agency, think doctors, nurses, social workers, physicians, assistants, potentially technicians, etc. There are those of agency. There are portable resources that mobile agents can go and get and bring back. So a nurse can go get an ultrasound machine. A nurse can go, or a physician could get an ECG for a patient encounter. A nurse's assistant could get a wheelchair to route someone around and bring it to a patient. By contrast, there are also fixed or static resources. So again, CAT scan, VQ scan, X-ray machine, etc. And generally you have multiple types of resources. Now, these types of resources define resource pools, and we saw that earlier. I don't want to belabor this point, but if we scroll down, we will see these various types of resource pools. And each of these so-called resources delineates a resource pool. There's a specification of the home location for that resource, the default capacity of that resource, absent increasing it while the model's running, say. How that capacity is defined, but it can be defined, say, by a schedule. Certain times of day, you can have more of them, certain times less. There can be none of this resource after a certain time. There could be shifts, some sort of group schedule that governs many such resources. There's and I'm not sure here. Yes, here we go. Under these parameters, there's an arrival rate schedule that indicates what's the rate of arrival of different agents. And you can also put in place a schedule that will delineate the availability of resources, whether resources are in fact available or not. Let's talk briefly, time runs on here. Let's talk briefly about major operators, major blocks of interest in this structured workflow language. I think you'll find them actually quite accessible. There are sources which go off with a certain rate or a certain set of rules that govern the arrival. Here we go. So here we go, a source, and you can have a rate schedule, a certain rate or an inter-arrival time or database-based schedule, or you can dynamically schedule, say, inject an entity into this. So this is for arrival of entities, which are going to flow through this workflow, right? Note again that you can have a rate schedule specified by the schedule. That's what we saw just about 2 minutes ago. Or an arrival schedule when they, I think that may be, when particular ones arrive. I'd have to check that. As you could say, location of arrival. And here there's some ability to frog things, say multiple agents arrive at once, etc. Syncs, not surprisingly, lead to agents departing the system. And again, within that departure, we would handle it different. I believe we'd use enter and exit if this is a hybrid model. So agents who wish to enter this we would have an enter at the beginning and exit at the end, so those agents wouldn't be absolutely deallocated or sort of deleted from the model. They won't disappear from the model. Here we have enter and exit there, and here we can. This is a bit dated, but this is the primary mechanism by which agents can, in a hybrid model, can enter and exit a workflow. We can select output. We can have a branch. In older versions of AnyLogic, it was shown like that. Here it's shown as select output here. Select output. And there we can route people on into different true and false possibilities, according to, and I apologize, I need to go find one here. I thought I had done that. No. Here, there's a certain probability that they will go the true way compared to the false way. And here, you could see this probably walk-in patient probability. This is true. That's going forward in this sort of forward side of the diamond. This is false. So they're routed this way if that probability is not true. So with this probability, it flips a coin. They go this way. Otherwise, they go that lower. You can also specify a condition. And you can start to see why I say there's not as much writing code here, right? You're characterizing predicates. You're characterizing kind of rules here, maybe a condition, maybe a probability. You're not so much putting in place code like we did for the histogram, for example, last Thursday during the lab. A key block is a delay. And sometimes that's combined in what's called a service block. But this would be one by itself. This delay, after they've kind of been admitted, they're awaiting the physician assistant here. They're awaiting a physician assistant, and it looks like a technician. Once they get both of those, they proceed to this delay block, which has a delay time given by this distribution. It draws from a triangular distribution with this minimum, this max, and this mean, and that many minutes. It will allow them to, they will be in this block for that amount of time, and then they will proceed along and release these resources. So they got the resources here needed to proceed, and they released the resources here. Or released the technician. They haven't released the physician's assistant yet. Okay. Okay. So I mentioned the resources. Critically, when an agent cannot reserve a resource when they're awaiting this technician and physician's assistant before getting worked up, when they're awaiting the X-ray machine, when they are awaiting to be triaged in the emergency room, they are in queues. They await the resource, and in awaiting the resource, they are placed in a queue. And that queue may be capacitated, meaning it's of fixed, some limited specified capacity, or it can be unlimited in capacity. And, as you might think, a waiting room might be limited in capacity in terms of people awaiting care, that there may be some limited space, and therefore you might, for the triage nurse, specify some fixed queue capacity. On the other hand, for other resources, you may have essentially no limit on queue capacity. So resources are living in pools. The idea is I am awaiting here some registrar. I am awaiting some nurse. I am awaiting some technician and some physician assistant. Critically, I'm not awaiting a specific one. I'm not going to require the same one I had last time, for example. Or I'm not insisting on a very particular one. I'm drawing from a commodity pool. So I'm awaiting this, trying to seize one. In order to do that, I may wait. I will wait often. And then when that's available, it'll be allocated to me and I will proceed. So once this is available, registrar or proceed to registration. Once the technician and physician assistant are both available, I'll go and be worked up. Notably, and this is rather important at a conceptual level, you can either seize each one by one as it becomes available and wait till the final one becomes available, or it's transactional, or it's atomic. You seize both at the same time. You need both to be available at the same time. You're not seizing them catch as catch can. This is very important because if one's not careful, one can have what's called a deadlock. So I seize the physician assistant and I'm waiting for the technician. You seize the technician and are waiting the physician assistant, and neither of us can ever make any progress. So either you have to be careful to seize them in the same order for everyone. I always seize A before B. Everyone tries to seize A before they seize B. Or they have this characteristic of seizing the whole set at once, not one at a time, not incrementally. Right. Okay. And I note that you can have different pools for different subsets of resources if you want. Resources are released once they are done. So you may release the technician back to that pool. And you'll notice that these resources, if mobile, can be told, like, go back to your home location, go back to your technician's room or what have you, go back to the room that you serve, or your waiting room for being called up as a nurse, or go back to the triage area or what have you. So there's this little language of these operators. Each of these operators has somewhat distinct little options associated with it. Some have, like up at the top here, there's ability to have different types of options. So these little green items here allow you, for example, the three of them, to specify prioritized resources. So like if there's a higher priority that comes through, I allow them to go to the head of the queue. I can customize the resource type. I can also potentially leave earlier if I have a timeout. So, for example, I can say, hey, I've been waiting 3 hours in the emergency room. I'm hungry. I'm afraid I'm going to get sick from people around me. I'm seeing no sign that I'm going to be admitted soon. I'm going to go home. And so you can have people leaving leaving without being seen by hitching up these little connectors to, and I believe it's this upper right one there, and have them routed around declaratively. Okay, I will note that attaching and detaching operators allow us to move people around together. You can attach and detach entities from you can attach and detach resources to entities. And so resource attach, resource detach, and that allows when the entity moves, when the entity is told, go to this workup room or this procedure room, this waiting area, that resource will go with them. If they're a resource like a portable resource is attached to them, say portable ultrasound, that will be brought with them to the procedure room or what have you. So the entity, along with any attached portable mobile resources, can be moved to a location. You can use the move to primitive for that. There's this move to block, which will move the entity somewhere. Alternatively, you can send a resource to a location by resource send to. You can send them to a certain room, send them to their lounge, send them to the ambulance entry area. So there's a fundamental distinction here between seizing a resource, which is about allocating that resource to an entity on the one hand, and you later release it. From the other, attaching and detaching a resource, which dictates whether the resource spatially goes with the entity. The first is the more fundamental one. It's about, is it allocated to the entity? The second is about movement. If the entity moves, do these things go with them? If we send the entity to a certain place, the VQ scanner room, the procedure room, to the waiting room, to the exit, does this resource follow them? Okay. We could, I have various elaborations on this that you can look at. I will just emphasize again that this is commonly coupled with a visual depiction in which entities move around. Locations are assigned as the home location for certain areas. We saw that earlier. We saw that these pools, for example, of resources, doctors are associated with a home location of the doctor's room. The ultrasound technician is associated with the tech location. The CAT technician here has a home location of the tech location. The registrar is in the registration room. The triage nurse here is in the triage room, etc. More than that, if we go up here with entities, we will move them here. They can enter via a walk-in area, and they can proceed. They move to, that's something you do to an entity. Resource send to is done for a resource. Here, they are moved to a triage room. And the triage room is a defined room within our system here. So we have within these areas, and I'm going to go here. If we go and look, we have these various connectors. And I believe it's in, and I should know this. Yes, these are various walls. There's considerable number of walls. And then there's here for example, the X-ray room, or the X-ray scanner one, or there's here various types of text, and I'm going to look for triage room. Well, these are rather voluminous. But you can go through these and find, okay, here's the X-ray room, for example, or here's the waiting room. This is the walk-in entry, etc. So resources associated with locations, with icons. They have here types of resources, and over time, types of resources. There we go. And if you zoom in, you will find that somewhere here, there is a little doctor icon, which at this resolution does not seem to be terribly identifiable. Well, that looks awfully vague to me. Similarly, there's a nurse icon, etc. Movement paths, we've seen those among these networks are associated with. We can have paths along which people can travel. Okay, I think I've given the essential features. There's more detail. It's possible you want to look at some of these other slides, but we've covered a lot of the essential features of what makes discrete event simulation a powerful technique. And to sort of recap, discrete event simulation is about resource-constrained movement along structured, statically defined workflows. Those are statically defined, but the routing along them can be based on patient characteristics, aspects of patient history, and this type of modeling provides an exquisitely expressive way of talking about these sort of movements along these workflows in ways that allows us to easily ask questions about if we increase the amount of resources available or place those resources at different locations, and therefore the movement times were different. Or at different prioritization strategies, or different orderings in which the workflow was structured, how would it affect the time that patients spend in the system, the waiting time, the waiting list length, the number of, say, patients leaving without being seen, the loss to treating. How does it affect the number of patients we see per day, the so-called throughput? All of these can be readily specified in this language of discrete event simulation. It is a language that's more specialized than that of agent-based modeling, or for that matter, that of stock and flow modeling, system dynamics, compartmental modeling. ABM and stock and flow modeling are very broad traditions covering flexibility for a vast number of different configurations. Stock and flow modeling is a smaller vocabulary that allows artful shaping of just a few pieces put together in judicious ways, can be very insightful. ABM modeling, a larger vocabulary that allows us to specify an incredibly vast range of models. Discrete event simulation is more focused on resource-constrained progression of entities along structured workflows with an eye towards assessing the impacts of resource availability, placement, workflow design, and prioritization on impacts on service length, throughput, availability, quality of service, etc. Very good. That's all we have time for in lecture today.